Welcome to a video on first order low pass filters. So in this video I'm going to look at how we get to the design equations for our filters, then at how to interpret the Bode plot, then we are going to do some designs and simulations, and the simulations will contain time domain, Bode plots and FFTs. So first off, how do we get to our design equations for these filters? So, a low pass filter is a capacitor in parallel with a resistor over here, and let's call that parallel combination Z. Okay, so Z is R2 parallel to 1 over CS, where S is just a placeholder. I'm working with Laplace, but it's basically just a placeholder for J2 pi F. So if you insert that and you're not used to Laplace, this might seem a bit more familiar. When I convert this into a more workable solution so that we can see a couple of things. Okay, so I'm going to jump to this table down here at the bottom, and let's see what happens if we change F. So since we're working with a low pass filter, with lower frequencies everything should pass, with higher frequencies everything should disappear. Okay, so let's first say that F goes towards 0. Okay, so I'm not going to divide by 0 anything funny, it's just going towards it. Okay, so with F going towards 0, this term will become smaller and smaller and smaller until it's not really anything to work with, and we have R2 standing over 1. So Z basically becomes R2, and our gain is R2 over R1, which is just an inverting amplifier like we're used to. Okay, so that is your first design equation for the pass band gain. If we move F towards infinite, right, this term will become much greater than 1, and we will be dividing R2 with a huge number. So we're not dividing by infinite, we're just dividing by a big number. So Z will basically become 0 at some point. And that means that our gain becomes 0. So this is describing a low pass filter quite well. Right. Second is our cutoff frequency. So this point right here is a virtual ground. Okay. And here we have this parallel combination in parallel with the output here. So these two is basically working upon each other to find our cutoff. So the typical way we would describe that is with time constants, and that would be just 1 over 2 pi R2C. R1 has no influence in our cutoff frequency. Okay, so the way you could see this is if V out is a low frequency, low frequencies will typically rather pass through the resistor, and we would find that we are working with a pass band. If V out is higher frequencies will probably move more through the capacitor, since the capacitor becomes a short circuit at high frequencies. Okay, so more of the output signal will go towards this ground here. Okay, so that is the low pass filter in terms of design frequency. So we have this one over here and this one over here if we're doing any designs. So the first problem will be after this Bode plot. Okay, so in terms of a Bode plot, The passband gain is at the lower frequencies. The cutoff frequency is here at the minus 3 dB point. So since this is 20 decibels for this one, that point will be at 17 decibels. And our cutoff rate here, so for every decade that we move, our gain will decrease by 20 decibels. Okay, so the first problem will be based on the Bode plot. So frequency in the passband, the cutoff frequency, and what happens in this cutoff section right here. Okay, so problem 1. A filter with a cutoff frequency at 1 kHz is required to remove higher frequencies. So I don't tell you this is a low pass filter, you need to know that removing higher frequencies is a low pass effect. Okay, the filter must have a passband gain of 20 decibels. Use a 1 kilo ohm resistor for the input impedance, and that is the design. So provide components for all of these. Okay, then I want you to insert the 1 volt signal at the input and evaluate the three conditions down here. So what happens with a 1 volt amplitude is provided at 1 kilohertz through this filter? What is V out? Same for a 1 kilohertz, same for a 20 kilohertz signal, provided that a 2 kilohertz has a gain at 13 decibels. Okay, so calculate the results and simulate the circuit. So pause the video there for a moment and attempt to design and see if you can figure out what these values should be. So the solution, we need R1 to be 1 kilo ohm because the input impedance of the amplifier should be 1K and R1 is the input impedance. Knowing that 20 decibels is 10 volts per volts, we can find R2's value. And we just plug in our R2 value and our cutoff frequency into this equation, and we can find our capacitor is roughly 16 nanofarads. So that is the design, and we will test that in the simulation a bit later. Okay, so the input frequency at 100 Hz is in the pass band of our amplifier. So we're inserting a 1 volt signal. So the 1 volt we just multiply by 10, so our output should be 10 volts peak. Right. If the input frequency is at 1 kilohertz, we're working at the cutoff. So that's a minus 3 dB point. So we should be working at 17 dBs, converting 17 dBs to volts per volts is 7.079 volts per volts. And our output should be 7.08 volts peak. Okay, this is also a good way to find the cutoff point for the amplifier. You insert a signal that's known to you and you multiply that by 0.707 and the gain, and you'll find that when your output is at this point right here, if you read off a frequency on your signal generator, that is your cutoff frequency. Okay, so just using this technique to find the minus 3 dB point. It's one that I usually use to test things in the lab. Okay, so the last one over 3 is if the input frequency is a 20 kilohertz, and we know that the gain is 13 decibels at 2 kilohertz, what is the output? So from 2 kilohertz to 20 kilohertz, that is a minus 20 decibels jump. Okay, so if 13 decibels is the gain at 2 kilohertz, minus 7 decibels will be the gain at 20 kilohertz. So we can convert both of these to volts per volts, and at 2 kilohertz our output will be 4.467 volts, and at this minus 7 we will be sitting at 450 millivolts peak. Okay, so let me jump into the simulation here and show you. So I went ahead and set up our filter, and I already did some measurements in the Bode plot. We will get to that in a moment. So first off, I set up our signal here for AC1. So that means that we don't have to deal with any strange dB conversions in our Bode plot. So always put this on AC1. The Bode plot for LT Spice does not check these voltage limits when doing a Bode plot. Okay, then for the transient analysis, I set up a sine wave with a 1 volt peak signal and at different frequencies. So I set up for the 100, 1K, 2K, and 20Ks that we are looking for. And then I use something new here, and I said dot measure. When we're doing a transient, I want to call the variable Vmax. Search for the maximum voltage for node Vout, which is this one over here. And that information will be written into the log file of our simulation. So I just wanted to open the log file here. So .open lpf problem1.log. Usually the log has the same name as the schematic. Okay, so first let's do the AC analysis or the Bode plot so that we can see what we're dealing with. So if I run this, I have to select and just close that thing. This is our log opening, but it's not needed. So if we click our input here, we have a 0 dB input right across the board here. So that means a 1 volt input. So AC as 1. We double click here. Just want to remove a phase. We can see that at the lower frequencies we have 20 decibels, so that's our 10 volts per volts. And if we open our cursor here, it's just a little bit below 20, but it's pretty much 20. So if we move towards 1 kilohertz here, we will find that we're at roughly 17 dBs. So that is our minus 3 dB point at 1 kilohertz. So that's our cutoff frequency. Here at 2 kilohertz, we're at almost 13 decibels. And here at 20 kilohertz, we're at minus 6.07 dBs. Okay, so those are the 3 points that we're going to use for our calculations. Alright, so if I close this, this is the measurements that I did before. So minus 6.07, I made minus 6.1. This is, for all intents and purposes, very close to minus 7 decibels. So there is a 20 dB jump between those two. So I already listed the gain. So if we do the transient here, it will throw out the voltages for all 4 of these different frequencies. So if we run it, transient, here we have it. It's almost 10 volts, 7.04 volts, 4.4 volts, and almost 0.5 volts. So close to the values that we calculated by hand, or where they should be. Okay, and if we plot the output, there's a 100 Hertz signal, our 1K signal, our 2K signal, and our 20K signal down there. So you can see the filter working in the simulation quite nicely. Okay, so let's jump over to problem 2. So the second problem here, I provide you a signal with 3 frequency components, 100 Hz, 1 kHz, and a 10 kHz, 0.1, 0.7, 0.5 volts peak for each. This is what the signal looks like. And I tell you to design 2 filters, both with a 20 dB passband, so you can use the 1 kilo and 10 kilo like in problem 1. I tell you to design this at 133 Hz to remove the 1K and the 10K. And in the second problem, to design for 1.3 kilohertz. This is to keep the 100 and the 1 kilohertz signals intact and just remove the 10 kilohertz signal. So need to design the capacitor for each and then do a simulation to find the Bode plot for each and do FFTs on the signals so that you can see how they reduce in actual size. Okay, so the capacitor is 120 nanofarads for 133 Hz filter, and 1.3 kilohertz will give us a 12 nanofarad. So there's just a decade between the components as well. Okay, I'm not designing these directly for 100 Hz or directly for 1 kilohertz because you want to keep those signals intact, so you just move the frequency on a bit by a couple of 100 hertzes. So this will help tremendously. So let's simulate these problems and have a look at the Bode plots and FFTs. So I went ahead and set up the 2 filters and also created a file with the 3 signals in it. So you can either download it from my tutor or go and watch a LT Spice video where I show you how to create signals. So we're first going to do the Bode plot so we can see that these 2 filters are working correctly. So let's run that. This should be for 1.3 kilohertz. This should be the 133 hertz filter. Let's switch off the phase. So let's go to this signal here, and at 150, there is our minus 3 dB point. Passband is 20. And let's go to the second signal here. And our cutoff should be at 1. 3. There we go. Move this one again. There is our 2 cutoff points. Okay, so they are functioning properly. Let's go over to the transient analysis so that I can show you what the signal looks like on the input side and on the output side, and then we can do the FFTs. Okay, so transient. What it looks like is you can see the 100 Hertz here on the outside. So if you have a power line issue in a circuit, you can also see the signal running on it. Then we have our 1 kilohertz here, and our 10 kilohertz looks like noise sitting on the 1 kilohertz signal. So the first filter should remove basically our 10 kilohertz signal right here. So you can see that the 100 hertz is still present, the 1 kilohertz is still present, and most of the 10 kilohertz has been removed. The second one here is the one that should remove both 10K and 1K. And you can see that most of 100 hertz is there, but there is still a little bit of a 1K left. And if you look at the points here, a little bit of a 10K remains. Okay, so if you want to get rid of some of these components much better, you need to go to higher order filters. But we can see that the elements has been removed. Okay, so let's go to this filter right here and let's do a FFT for it. Right, so V out and V in. We want to do both. And if we have a look at the FFT, the green signal is the input. So there's our 100 hertz signal, there is our 1K, and there is our 10K. And if we have a look at this filter, it is the one that is supposed to remove most of a 10K. Okay, so you'll see that the 1K is being amplified, the 100 hertz is being amplified, but the 10K is being suppressed. It is much smaller than the original in the FFT. Okay, so let's close these. Let's do the FFT for the second one here. Okay, so we need to have both selected, and let's say FFT, both of them run. Okay, so you can see the 100 hertz, the 1K, the 10K. The 10K is much larger, the original signal, than the output. So it is being suppressed. You can see that the 1K is being suppressed and our 100 hertz is being amplified. Okay, always remember that these dB scales here is the RMS voltages, not the peaks. Okay, so the FFT describes our signals, so we can see what is happening to our signals from input to output. And the Bode plot describes our filters functioning. Okay, and that is it for low pass filters and simulations on low pass filters. Thank you for watching.